The last data analysis for us to go through is a regression analysis or regression curve. So mainly we talk about calibration curves. So we'll use an instrument and we will have you make up solutions of various concentrations. And then you have to run it through the instrument and you're going to get some sort of signal, some sort of response. And you have to plot it against each other and you get some sort of line. When you get to J. Mycroft's class, he's going to teach you all about this. So a limit of detection, limit of quantification, limit of linearity, the dynamic range. And essentially, we need this relationship between signal and concentration. So we need to create an equation that matches this line. And that is where the regression comes in. So we call it a slope. We've got a variety of different things, calibration curve, standard curve. But essentially, it's a relationship between these two values, an x value and a y value, and we'll do a regression analysis to see what this line is, and we'll even do a best fit to the line, which is called an R squared. So typically, using a linear regression analysis, it yields a model called y equals mx plus b. They use y naught here because it's the y-intercept, but just note that y equals mx plus b is it. B is the intercept here, the m is the slope, x values here, y values here, and that creates this equation. So what we're going to do is we're going to work with a data set that students have used in the past. Now we are not doing UV vis analysis this semester, not in our course, but I took the data set from last year and we're going to work on this. So here's concentration that students developed. Here's three absorbance values. We need to take the average of these values and then we need to plot it against concentration. And we've got up to 56 data points. You'll see there's some missing values here. So we're going to go through the data set, we're going to sanitize it, and then we're going to analyze it by doing a regression. We're going to get ChatGPT or Copilot to help us out. And the easiest thing for us to do is really just copy this. If it's hard to copy the data here and get it into Copilot, then you can copy the original file in the CSV, get it open in Excel, for example. I don't have the specific one, but here's a box plot. I could highlight this whole data set, right click, copy it, put it into Copilot or ChatGPT and say, "We're using this data, do this." But there's more information I want to add to it as well when I use Copilot. Things like what the file name is, and what specifically I want, what columns I want analyzed, that kind of thing. The fact that I want to do an average. So all of that information is what we're going to work on for this regression. So let's start at the basics with the regression line. Let's say we've got x and y values that look like this. Just the y's here, just randomly determined from this. And we want to do a regression of that. So we've got multiple ways of doing this, and every library under the sun seems to have a different way of doing it. So let's explore some of it. The first one here, we're going to use pandas, and we're going to use a library called stats models. Just note what they're calling them in as. And they're taking our data set that we just had, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and applying it to x. So there's a tuple, I believe, or a list, and y is given to this data set here. It's creating a data frame from this. Normally we would call in a data frame from a CSV file, but they're creating a data frame from the x and y values. And now based on the data frame, they're adding a constant to it. So they're calling it, to the data frame here, x and y, we're going to have something called constant. And then now stats model as SM is going to do a calculation called add constant. So based on the x values, and I assume the y, it's going to create a constant. Now it's going to create a model. So there's a variable called model, and this is what is it called? Original least squares. Uh, it's a least squares, original or ordinary least squares result. And so based on the function of y, or sorry, the column of y and the column of x and this new constant that's been created, we're going to create a fit. And what this does is it prints out the model, the entire data set here. It's not a curve, but it's still the same information. There's our R squared value right here. There's a adjusted, but this is the one that we would normally see in an Excel file. So based on the y variables, number of observations, the various calculations, and be interesting, I think this is the slope here. And so this is our B-intercept potentially. So I'd have to go in and make sure about this. But there's more data that comes out of it that I am actually not familiar with. So I'd have to actually go through, put this back into ChatGPT and try to ask questions about it. But I believe these coefficients are the data that are coming out that we're trying to get, potentially. And that's it, unless this is the slope, but I don't think it is. So I think this potentially is our slope here, but I'm not sure. You would figure it would be, yeah, it's 1 to 1, so it's about here. It's close to, it's got to be close to this one. So the hope is that this is it, and I'll try to clarify that a little more. The other option is we try to draw it out. And so I've got another one where I can call in the same file, and this one treated it different. So it actually said this is a variable called x, and here is the data. Here's a variable called y, and it used SciPy instead. So we used over here stats models. Here we're using SciPy. And again, if we had to use Seaborn, then we would have got a different code to do that. And you see there's multiple ways of doing it, and all of them kind of give a correct answer. The only problem out of this is now we get the plot, which is great, but we're not getting any values out of it. So what we'd like to do then is modify either of these codes to say to this one, okay, now create the plot. We'd probably see some major changes happening here in order to actually plot the data. And here we seem to be using X and Y on something called a regression line. It actually creates the slope here, but we've got this stats line regression, and so there's possibility we might be able to pull this data out here because there's it wants you to get a slope, an intercept, and an R value, and we might be able to print those out. So let me just see if we can do that. So after we plot the show down here, I'm going to see if we can print this stuff. So I'm going to print slope. Let's just run this and see what happens. Ooh, there it is. All right, so the data's there. This seems to be one of the easier ways to go for the basic one compared to the other one, I think. So I want to print out the intercept. Let's see if I printed this right. Yep. So, and then what else we got here that we want R value? So I'm just going to copy this one. And we'll run this and see what we get. All right, so 0.997. So let's compare to the previous example. There's a difference between them, I believe. So the slope here is 1.0563. The slope here, 1.0563. The intercept, 0.07488. 0.074. Oh, this is rounded. So the values are the same. That's great. And the R value here, 0.9975. So 9978 rounded up. So that one's a little bit different. So this one here, the fit is, so that's a 995 and this is a 997. So this one's claiming that the fit is better here, just slightly better than on this one. But otherwise the resulting slope and intercept are actually the same. So that's good. This one here is, to me, it's a little bit easier and straightforward to do it. You just need to define your X and Y values. You could get these from your column. So if there's potentially, we could do a group by function and then apply variables x and y to the group by function and then pass those through this stats line regression as x and y, and hopefully that would actually do the work for us. Obviously here I do not have any null values and no zeros or missing data at all, and so we would need to make sure that the data got scrubbed before it went through this or it'll cause an error. This is what we're trying to get from here. So using this equation, try to plot something like this using our large data sets. So I got two versions of it here because of some learning as we go along. And I just want to point out that up here we're using SciPy and Matplotlib, but we're going to incorporate NumPy into this and something else. So we've got pandas, NumPy, SciPy, and Matplotlib because we needed pandas to actually pull in the data frame. So the first thing we do, read in the data file. So it's going to be the regression data, this one right here that we've got. And we're going to drop any null values. The regression analysis doesn't work if there's missing values. And if we go through this, we'll see that we've got one missing right there. And we got an entire row missing right here. So this wouldn't have worked. So we're going through this, and so we're dropping all of those. First thing we need to do is take an absorbance, an average absorbance of columns 1, 2, and 3. Sorry, of these three absorbances. So we're going to create a new column here based on that. And that is going to become our y-axis. And then the x-axis is essentially all of the work that's been done on this concentration. So just getting rid of all the rows where there was some missing values. And so when we use this equation here, so the stats.line regression, uh, x is the concentration and y is the average absorbance. And we can then spit out the slope, the intercept, the r value, which is our r squared value, and a standard error as well. And when we do that, we're getting we're getting a value that's pretty bad. So our slope, first off, is negative. Our intercept is up here at the 0.4. Our R value, so this value is a negative. So this line obviously doesn't fit at all. And our standard error is 39. So it's a huge, huge, huge error. So to create the plot, then we're going to plot concentration versus average absorbance. We want the data points on there, so we got a label for data points here in blue. And we're going to have the plot of the concentration. We want the intercept plus the slope times the concentration. So this calculation, this value here is going to be multiplied by the concentration down here and create our line. And it's going to be called line of best fit. So this is going to be red, line of best fit. So this work right here is creating this red line right there. So a scatter plot is created. That's all the blue stuff right there. That's with this line right here. And then the red line is created right here because we've already done the linear regression up here, and we're going to use the values. All of this information, slope, intercept, R value, P value, standard error, all of that comes through into here. Well, the intercept and slope do. And then we label it concentration, average absorbance. We put a legend in there, and then we show the plot. So the problem here is this point right here. This is causing our error. This is causing everything to be thrown off. This is our data set. This is a line of best fit, but because of this one data point, it is skewing our data significantly. And this thing here is 10 times greater than any other value here, and it's causing havoc. So what we need to do is on our data set here, so when we pull in the concentration values, we need to have another row up here, so another piece of code. So after we drop all the null values, we also need to get rid of any rows where the concentration is greater than a certain value. And I'm choosing this value right here, so it's pretty free and clear that anything above here is wrong. And so we'll incorporate that into it. So a new line right here, and we'll see what happens to the rest of the data set as soon as we put that in. And that's what this one is here. And so now we've got the read the CSV. So all the files are the same, or all the libraries coming in are the same. We're going to read our CSV file. We're going to drop NA, and there's our new line right there. So the data frame then, or after we've dropped this, the new data frame with concentration less than 0.004, or sorry, anything greater than 0.004, remove those values. And now the rest of the thing is the same. So there's our absorbance, which is going to be our Y value, our concentration, which has been affected by this. So any values greater than 0.004 and any missing values will be removed. So that now has our data set of X values there. And all the rest of this was exactly the same. The only thing I changed was I put in R squared and standard error as well. And then the same plot. So a scatter plot just of our little blue data points right there. So the concentration and absorbance, there it is. You can see we still got a few points that are off. And we're going to then do our red line of best fit. So that will be concentration, and then the intercept plus the slope times the concentration values. That's going to be our red value like that. It's going to be a red color, and we're going to call it line of best fit. We're going to have an X label of concentration, Y label of average absorbance, and we're going to plot that. And here it is. And so this is what it looks like, and it's probably as good as we're going to get. So we got a slope here of 555. We have an intercept of about 0.19, so about right there, so that looks correct. The R squared value is still really poor, so 0.53. And what we would need to do then is start to take a look at getting rid of some of these extreme points again. So we might consider maybe getting rid of anything above 0.014. we might want to get rid of anything above 1.1, and that would remove these data points and these data points, and we'll see that the fit will get better. We do need a reason to get rid of these. We can't just sort of say that they're off. But it turns out that in the instrumentation that we use, there's no values that we can get essentially really above 1. We've got it designed so that none of the instruments, none of the concentrations will be above 1. So these values right here are out of whack. This is someone did a concentration error or something when they were actually doing their work. And this one here, the absorbance value is too low. It looks like they put in the wrong value. This would be 1, 3, or 5 milliliters of stock concentration. This looks like it should have been here clustered in this in this one. And if we look, this cluster right here is from our 1 milliliter stock. This is from 3, and this is from 5. The spread gets bigger and bigger, and it almost seems like the line should be kind of going this way. So we'll take a look and see what happens if we start to remove some of these values as well, and what happens to our line of best fit. So by changing the one concentration value here that we're removing, instead of 0.004, I just put in 0.0014, and it got rid of that one data point that was over here, and we can see that the best fit line now, the slope is 773, the intercept is 0.11, and the R value has gone up from 0.57, whatever it was, to 0.67. So it's getting better, and so the one thing we'd like to kind of remove here are these values if we can see, and just leave it at that and see what happens. So we're pruning the data, trying to get a best fit here. The hope is that we've got some reason as to remove these to do that. If we've got a reason to do it, if we look at the data set and see that we have a reason, then yes, we can remove them. If we don't have any reason to remove them, then we need to keep them in. As bad as this data set is, we might need to keep it in. And if it is that bad, that warrants redoing the entire experiment again because the result was so bad. So let's see what happens if we get rid of these here. So I'm going to put in something, or try to put in something where I can get rid of the absorbance values that are greater than 1.2. Okay, and so what we've done now is after we've done the average of the absorbance, we've removed any rows with absorbance greater than 1, 2, and 1.2. And we see that the best fit is better. There's a couple of values here that are still off. Again, it looks like this absorbance value is supposed to be here, so that someone wrote in something that was wrong. In fact, the concentration of this is so low that it's not possible that this was in here, that an absorbance value this strong would come from a concentration that was almost zero. So obviously someone put in the value wrong. So there's one more that we could potentially get rid of here. But in the meantime, we see our slope now. So after we remove anything greater than 1.2, we can see now that the slope is 749. The intercept is 0.085, but this is the one here. The R squared value is 0.80. So we keep getting closer and closer to 1. Now with a very, very large data set like this of random of data from a series of students, we're going to find that our R value will not get to 1. So if you were to do the work yourself as an individual, you can find that your value here is going to get better and better, but when we're relying on several, in this case, 15 to 20 different students all doing the same work and compiling their data, this is the kind of random error that you're expecting out of it. And this is the type of thing that will happen in industry as well. So I'm going to try to add in one more piece of code to see if I can get rid of this value. So I might remove any values under a certain amount here under concentration. So up here with the concentration, any values greater than 0.14, and I'm also going to remove any concentration values under a certain amount here as well that I will determine by going through this regression data. So the first thing that I did then was it was too hard to figure out what the smallest value is. So that one that was over here. So I added something in right here. So I wanted to find out what's the minimum concentration, what's the lowest value here out of concentration. So I threw that in there. So on the data frame concentration, tell me what the minimum is. And axis equals 0 refers to the column. So for the entire column, what is the smallest value? And if it was axis equals 1, it's on the row. What's the smallest row? So I want it on concentration, and what it did is it spit out a value here. So that was the concentration that was the smallest one that was causing a problem. So what I've done now is gone back up to here, and I've now added in, instead of just getting rid of values that are greater than 1.2, I also got it to get rid of values that were lower than this value, but I actually upped this a bit. So instead of 1.651 times 10 to the minus 5, I did 1.70 times 10 to the minus 5. So anything less than 1.7, I got rid of. So that would be way down here somewhere. And so it got rid of that value. So this one here is about 1.7 right here. So we see we got an R value of 0.80 currently. We're going to try to remove this value, which appears to be this one right here, because we defined the minimum of the concentration. It spit out this right here. And this definitely seems to be an error. There's no concentration that should be this low. Again, this is 10 times lower than anything anyone has done. And so it's clear that what they've done is that there was an error in the calculation, and this probably should have been up here in part of the 5 milliliter volumetric standards. So let's remove this. So what I'm going to do then, the next thing right here is I've added in that remove this below 0.17, 1.7 times 10 to the minus 5. All the rest of it's the same. We'll see what happens to the slope. So here we go. So the slope now has changed even to 823. The intercept is 0.036. This is the one that we're looking at. So we've gone from a 0.80 on the R value here to a 0.87. So we're getting closer and closer to 1. And now our new minimum value, because I kept it in there, is 0.000126, but everything here looks good. As you can see, we can keep pruning, but at some point we have to stop, like, because there's no reason as to why. This seems to be that there was an error here as well in the calculation, that the concentration here is greater than anything we've ever done. So again, we can start pruning and pruning, but at some point you got to stop. And this right here, we've got a value of 0.87, so it looks pretty good. So we might just finish this here with this as our value. So with 823 as our slope and 0.036 as our intercept down here, we might just stop here. You can go further, but again, we need a reason to remove these if possible. But there we go. So this is, to go over it again, reading in using pandas library, NumPy, SciPy, and Matplotlib. We're reading in our data frame of the regression. We're dropping any of the missing values, and we've pruned the data right here. So anything that was concentration-wise, anything here that we felt was out of whack, we removed it using this line here. So anything less, or sorry, anything greater than 0.014, 0014, and anything less than this value, we removed that. Then we took the average of the absorbances, and once we took the average of the absorbances, we found that one of the values there was, or two of the values were actually great, and they shouldn't have been that high. They were a value of 1.4, which was not possible with the data set. Here we can see everything is below 1, which is the way that the data was aligned for your lab. And now, because we pruned all this data, we can now do the linear regression. So we're using the SciPy stats to do a linear regression based on concentration and absorbance that we've pruned here. And so there's our X, there's our Y. And now we can print out, after this calculation, the slope, the intercept, the R value. We also did the standard error. I didn't do the P value. And here I'm printing out the minimum again. So we can remove this because it's not worth our, our value anymore. You can remove it, and that's it. So we've essentially defined everything. Now, obviously we're not getting this on the plot, and that's fine for what we're doing, because when you submit these, you'll submit the Jupyter Notebook file, which will have this information right either above or below your slope and data points here like this.